Hi and welcome to MSc. In this video we're going to be looking at an example of formal charge. We're going to be looking at the cyanate ion to determine its preferred Lewis formula. So to determine the Lewis structure that's preferred here for the cyanate ion, OCN negative, we are going to use the formal charge formula. This was covered in a previous video that I did, so if you've not watched that video yet, go and check that one out and then come back and look at this one afterwards. What we have here is we have the number of valence electrons, we have the non-bonding or lone pair, sometimes this will be L, and then we have the bonding electrons divided by 2. So there are actually 3 reasonable ways that you could try to draw out the cyanate ion. I suggest you try pausing the video here and try drawing them out and see if you come up with the 3 different ways that you can draw this structure. So the first way that you might have found is the oxygen bonded to the carbon, triple bonded to the nitrogen. Nitrogen has 1 lone pair, oxygen has 3, and because it's a Lewis structure or Lewis formula, you'll put it in square brackets with a negative. So that's one option. I'll put a line here to divide the options up so that we don't mix and match them. The other way would be to double bond the oxygen to the carbon, and then we have the nitrogen. Both nitrogen and oxygen in this scenario get 2 lone pairs. Again, it's an ion, so you have to draw it out like this. Both of these examples, we have everything obeying the octet rule, so nothing seems to super separate them at this stage. The last example is where we have the oxygen triple bonded to the carbon, single bonded to the nitrogen. Nitrogen gets 3 lone pairs, oxygen gets 1, and again it's a Lewis formula, square brackets, and the charge on the ion. Now, of these 3, I hope that perhaps you could determine that the last one is least likely because of the triple bond on the oxygen, which is pretty rare. And so that's probably one that you might be able to throw away right away, but we're working through it, and we're going to work through all these examples, including this one, to be able to officially rule it out. So to determine the preferred structure, we have to do this formula for each atom in each structure. So I have to do this 9 times. So to start off, we'll start the formal charge of the oxygen here. It has 6 valence electrons on oxygen. Here it has 6 electrons that are non-bonding, right, lone pairs, and it has 2 that are bonding, but it only has control over 1 of them. So 6 minus 6 is 0, minus 1 is what we're left with. Then we can repeat this process, the formal charge, for the carbon. Well, carbon has 4 valence electrons. It has 0 lone pair in this case, and it has 8 bonding electrons. It controls half. So this will give us a formal charge of 0. And then lastly, we have the formal charge on the nitrogen. Nitrogen has 5 valence electrons. In this scenario, it has 2 lone pairs, and it has 6 divided by 2, 6 bonding electrons. So this will be 0 as the formal charge. So this one gives us a change in formal charge from maximum of the 0 down to the minimum of -1 of 1, right? An absolute change of 1 from most positive to most negative. All right, let's repeat this process now for our second option. So formal charge of oxygen, I'm going to go a little bit faster. It's 6 valence electrons minus 4 non-bonding minus 4 over 2. That's going to give us a 0 formal charge. Formal charge on the carbon, and you'll notice that this carbon here has the same bonding and lone pair structure as before, right? No lone pairs, 8 bonding electrons, formal charge of 0. And then we have the nitrogen. And the nitrogen here, 5 minus 4 minus 4 over 2, that's going to give me a value of -1. So this option, just like the first option, has a change in formal charge from most positive to most negative of 1. So far these seem pretty equivalent. So let's look at this last example, the one that maybe we had deemed least likely from the get-go. It has 6 valence electrons on oxygen, 2 here that are non-bonding, and 6 over 2, which is 3. And so we're going to end up with a formal charge of 1 on the oxygen. So that's different than the other ones. The carbon is no different than the other ones. 4 minus 0 minus 8 over 2, which is 0. And the formal charge on the nitrogen, this one looks like it's going to be different. This is 5 minus 6 minus 2 over 2, which is going to give me negative 2. So that means this one here has a formal charge difference from the +1 to the negative 2 of 3. So we can definitely eliminate this one as very unlikely. Doesn't mean that I might not find some of it in a sample, because these all might just resonate between all of them. However, this one, less likely to show up, right? Electrons are not actually fixed in location here. They can move around a bit. So I might find a small amount, but definitely not the preferred structure. These two look, based on the formal charge calculation, like they're fairly equivalent. But you have to remember there's two pieces. We want the smallest change in formal charge from most positive to most negative. But we also want to have the negative formal charges on the more electronegative atom. So this one has the negative on the nitrogen. This one has the -1 on the oxygen. Oxygen is more electronegative than nitrogen, making this the preferred structure over the other one. Again, it would probably resonate a little bit between both, and you'd find some of this in the sample, but I would imagine that this one would be the preferred one for the cyanate ion. I hope this quick run through of this example of using formal charge for cyanate has been helpful. If it has, please consider liking this video and subscribing to the station. And as always, thank you so much for listening.